So this lecture is about geophysical parameter retrievals and space-based data products for weather and climate studies. Now I will just give a brief introduction. Actually, introduction is not needed, but then also I will briefly introduce the subject. That what are the products we want from satellite, or what are the products which we want to the state of atmosphere at a particular time, and climate is the average of this atmospheric state over long term, okay, over a long spatial as well as temporal temporal scale. Now these elements of weather and climate, or that is the atmospheric state, they are air temperature, that is temperature at different level in the atmosphere, not only surface but also different height in the atmosphere. Then air pressure at different layer in the atmosphere, atmospheric composition, the composition of various gases which are important, like water vapor, ozone, carbon dioxide, and various other trace gases. Then clouds. And clouds, that defines the weather system, like whether there will be rain or no rain. That is the mass of tiny water droplets. And they also have sometimes ice crystals over cloud. That is called cirrus clouds. Then precipitation. That is the rainfall. We call it when it is in a liquid form, or snow, ice. Okay. Then wind. That is the transport of the moisture from one place to another place. That basically is driven by wind. Okay. Then radiation. Radiation is basically the source of energy in our Earth and atmospheric system. So these are basic parameters, or very basic element of weather and climate that we need to study to understand the atmosphere and to do weather prediction. And how we can derive these elements or these parameters from satellite, that we will be discussing in today's lecture. Now we begin with why we need satellite. So satellite, basically they are required to monitor the weather events. First thing is monitoring. So if you see this right side, this image, you can see a cyclone approaching our Indian landmass over around Odisha or West Bengal. So before satellite, there was no mean to know whether there is a cyclone forming over oceanic region, and where it will be moving, and which part of the earth it will be hitting. Okay, so with the advent of satellite, we now know very well in advance, in 4 day, 5 day, or even 1 week in advance, that there is a cyclone formation taking place over ocean, and which direction it is traveling, and which region of the land we need to give the warning, so that people can avoid disaster. And that is the monitoring. And then other thing is whether this prediction of weather event. Now the second thing is prediction. That is, we want to know what will happen in future. Right now we know that there is a cloud system moving over different part of this ocean or land. There is a cyclonic storm taking over the ocean. Now where it will move in next few hours to few days to few weeks, that comes under prediction of these weather events. Now there are various scales of weather prediction. And in nowcasting, that is up to a few hours. Okay, you also sometimes you want to know that what will happen during next 1 hour, next 2 hours, whether you can travel outside, whether you can plan some sports event, or some similar other things. Now short range is up to a few days, like 1 to 2 days. Then medium range, that is few days to a week. Extended range, that is from 1 week to a month. And seasonal forecast, that is from few months to the entire season. And then there are climate scales, when we want to see the impact of climate change on, say, temperature or rainfall, or any other parameter. So there are different the scales of weather prediction, and we need the data for all these this weather prediction. Now, what are those parameters, or what are those data which are required? Now, for nowcasting, when a weather forecaster, they want to understand how is the atmospheric state at a particular time, they analyze meteorological charts. And meteorological charts consist of the contours of pressure, temperature, humidity, wind speed, and direction at different places. So based on those meteorological charts, they can predict what will happen during next few hours. Okay, and these charts, these data comes from surface observations as well as upper air observations, like radar sonde, where you can get temperature and humidity profile at different layer in the atmosphere. Now, weather for shorter time scale. Now, suppose you want to know how will be weather during next few hours over Dehradun or over Delhi. So for that shorter time scale, it's influenced by regional atmospheric state. That is, atmospheric state around Delhi, okay, maybe a few 100 kilometers to few thousand kilometers. May not, because for few hours, the weather event taking over faraway places like America or Europe may not influence within a few hours of time scale. So your data requirement for shorter time scale will be regional. But if you want to do weather prediction at longer time scales, like a few days to a few weeks, then global atmospheric state is important that you need for your numerical weather prediction model. So in that case, your data requirement is global. And here I'm giving just example here for numerical weather prediction. You have a numerical weather prediction model solving mathematical equations, and those equations, they are driven by physics of the atmosphere and of the atmospheric system. Now, when you divide entire world or entire globe into various grids and in horizontal as well as vertical direction, you need those data at each and every pixel or each and every grids. So those data, are you can derive from surface observation as well as satellite. Now, what are those parameters which are required? So for example, if we want to have an NWP model, for atmosphere, you need wind at every grid, okay, at various altitude in the atmosphere and over entire globe, ocean as well as land. Then you need upper air temperature, you need surface air temperature, sea level pressure, upper air relative humidity or absolute humidity, that is water vapor amount in the atmosphere. Then precipitation, the clouds, and liquid water content in the atmosphere. So these are some of the important parameters that you need if you want to do weather prediction. So these are atmospheric parameters. Similarly, oceanic parameters, you have ocean currents, upper ocean temperature, that is sea surface temperature, sea level topography, upper ocean salinity, sea ice, and various other parameters over ocean. And then similarly over land and water, you need topography or elevation, land cover, okay, and land type, surface soil moisture or soil wetness, soil structure, vegetation cover, water runoff, and various other parameters which you can see from this list here. So these parameters, all these parameters are required to make a coupled system, a coupled model comprising of land, atmosphere, and ocean, and interaction between all these components. Now I will tell you how these data are obtained. Traditionally, these observations, you can get them from land-based systems, airborne instruments, as well as ocean-based instruments. Over land-based, you know very well that there are automatic weather stations installed by various Met or agencies. Like IMD in India operates several AWS over entire Indian region. Similarly, there will be AWS over entire globe operated by other meteorological agencies of different countries. Then you also have Doppler weather radar, which can see the approaching storm and the storm intensity. Then there are microwave radiometer. They are also now these days installed at various stations, which can give you vertical temperature and humidity profile in the atmosphere. Now, similarly, airborne, if you want to get the vertical temperature profile and humidity profile, you have to have a radiation type of instrument where the gas-filled balloon, it lifts in the atmosphere, and this instrument fitted at the bottom of this balloon, it measures temperature, wind, and humidity and other parameters, whichever height it is ascending in the atmosphere. Then over ocean, you have this type of floating structure, floating buoys, and various instruments installed in that. So over ocean also, you have so many buoys installed, operated by various countries. And then there are ship-based measurement. Wherever ship is moving, ship also makes a measurement of different atmospheric and oceanic parameters. But to complement that, because the data obtained from these other platforms is not sufficient, so we also have space-based system like the satellite, we call them. So there are geostationary satellite over different geo-ring operated by different countries, and then there are polar orbiting low altitude satellites that also operated by various countries and provide data on atmosphere, ocean, and land. And these data, these are meteorological satellite. So by WMO has mandate that all the data acquired by any country should be shared freely with different weather agencies. So data like IMD also receives data from various satellites operated by global satellite operators, and we also provide our data free of cost to different different countries. Now you can see here one example that if you have AWS over this entire globe, so AWS you can see red dots over land, and over buoys, over ocean also you can see few of the dots there. So it only covers land mass mostly, and over ocean there are large data gaps when we are talking about this synoptic measurement. And then there are buoys over ocean, then radios only over land, which makes upper air observations, then pilot profilers and aircraft measurements. So you can see a large part of the globe is void of observations. So accurate weather prediction will suffer from these type of measurements. But satellite, they provide equally good this observations over entire globe with same efficiency. You can see these are the polar orbiting satellite making these many observations in one day. So one day, 8 ops can cover entire globe and provide you temperature, humidity profiles of the tropical region. But the polar regions are uncovered from geostationary orbit. So there are various other instruments which makes observation over different part of the world. Now a brief about remote sensing of atmosphere, how we get these different parameters which are important for weather and climate studies. You see here the first this one, how energy is distributed into our Earth and atmospheric system, and how the radiation travels. So the primary source of radiation is sun. So solar radiation primarily coming in visible region, that is from 0.4 to 0.7 micrometer, that enters into atmosphere and gets scattered back by the atmospheric gases and aerosols. Some of that gets reflected by cloud. Cloud is a strong reflector for this visible light. So almost entire this visible radiation can get reflected back to space if there is a cloud. Then even the amount of radiation which is reaching Earth also gets reflected by Earth's surface, and that depends upon albedo of the surface. For example, water surface has very small albedo, so from ocean there will be very less this reflection of the solar radiation back to space, whereas over desert and over other type of land regions there will be relatively larger this reflection. Now this is the solar radiation interaction. But if you are talking about emission, so this part of solar radiation, visible radiation, which you call, that gives you information only about the different type of surfaces. If it is highly reflecting surface, you can say that this is cloud. If it is very low reflecting surface, you can say that this is water or ocean. If this is medium reflection, then you can say that this may be vegetated area or desert. So based on that, you can classify or you can get information about various type of surfaces. But they do not give the important information about atmosphere, that is this information about the temperature and information about various other trace gases. So to get that information, we have to make measurement of the emitted radiation. So Earth and its atmosphere is also emitting radiation, and that radiation primarily gets emitted in the infrared. The peak radiation is of the Earth and atmospheric system is around 10 to 12 micrometer, and that also that is called as atmospheric window, because most of the infrared radiation, it's a 10 to 12 micrometer. The absorption by atmosphere is very, very less. The absorption will be there only when there is cloud, but if there is no cloud, there will be very less absorption by the atmosphere. So if you are having a satellite at the top of atmosphere, it can make measurement of infrared this radiation or microwave radiation which is emitted by Earth's surface and its atmosphere. Atmosphere means this emission by various gases. Now when you can measure the emission by surface or emission by various gases in the atmosphere, you can get the information of temperature and amount of trace gas in the atmosphere. So that is very, very important information which satellites provide through remote sensing. So in remote sensing, specific questions, so you can keep that in mind. Now in remote sensing, satellite sensors for met applications, there are two types of sensors. That is passive sensors, which measures this reflected visible radiation as well as emitted infrared and micro radiation from Earth and atmosphere. Whereas active sensors are those sensors where the source of energy is on this satellite itself. Satellite is sending those microwave pulses or like LiDAR, visible pulse towards Earth and atmospheric system, and then measures the backscattered or reflected component of that electromagnetic energy. So those type of sensors are called active sensors, where source of energy is in the satellite. Other part of thing, you can say that for visible reflection, the source of energy is a sun. For emission, the source of energy is emission from a surface or atmosphere. Okay, so the passive sensors are like visible, infrared, and microwave radiometer or sounder. Whereas in active category, we have a scatterometer, which measures backscattered energy, and an altimeter, which also sends microwave pulse towards Earth's surface, and then measures the time taken from total time taken from satellite to Earth and Earth to back to satellite. So by that it measures height of the surface. Then there are various other instruments like radio occultation, sounder, and LiDAR, which also comes under active category. Now this only I have already discussed that to make measurement of atmospheric parameters, okay, or surface parameters, you have to study the solar reflected or backscattered radiation as well as emitted radiation from Earth and its atmosphere. So you can see here at the top of atmosphere, if you see that this is the Planck's black body curve corresponding to solar radiation. So at the top of atmosphere, you see that this is just like this Planck function. But when you put that radiometer at the Earth's surface, so Earth's surface, you will not see any of the radiation which is coming in this region, and that is the ultraviolet radiation part, which is basically scattered and absorbed by the ozone layer. Okay, so at the Earth's surface, you only find you will only get the radiation which is coming in, under this solid this curve. And there are various other absorption lines which are corresponding to water vapor in the atmosphere. So even in the visible or near infrared region, there are strong absorption due to water vapor and oxygen at different part of the electromagnetic spectrum. And these absorption bands helps in determining the amount of those gases in the atmosphere, like oxygen and water vapor and other gases in the atmosphere. And if you see, if you want to see what are those gases which are absorbing in the atmosphere, so primarily it is water vapor which absorbs radiation passing through atmosphere. So you can see in visible region, you can see that this is around 1 micrometer. So visible region, there is weak absorption because of water vapor. And then when you move to short wave infrared, mid wave infrared, and infrared part, there is very strong absorption because of water vapor. You can see this part. There is very strong absorption from 6 to 8 micrometer. And then there is a continuum beyond 20 micrometer where water vapor strongly absorbs radiation which is passing through atmosphere. But in between, there are various regions where water vapor is not absorbing. Okay, these regions, those we can call as window. But then there are other gases which are also absorbing radiation passing through the atmosphere. Other primary gas is carbon dioxide, which is having a strong absorption from 12 to 15 micrometer, with peak at 15 micrometer. Okay, and then there are other absorption bands like 4 micrometer, 3.5 this micrometer, 2 micrometer, 1.5 micrometer, and like that. Okay, so there are, you can see in this curve that there are various absorption bands because of water vapor, oxygen and ozone, then methane, nitrous oxide, and this last one is not an absorption, this is Rayleigh scattering. So Rayleigh scattering takes place predominantly in visible or ultraviolet region, and that is the primary region. This much solar radiation is cut off from reaching Earth's surface. Okay. Now, if you see this Earth's radiation, if Earth was emitting and there was no atmosphere, at the top of the atmosphere, we will be reaching still this Planck function. We will be receiving radiation as per the Planck's function. But when you keep your radiometer at the top of atmosphere, you do not get this type of spectra. You get strong absorptions at various wavelength region. Okay, and then there is very less absorption at certain wavelength regions. These wavelength region where there is no absorption, Those regions we call as atmospheric window, and we study we study land surface features like SST, vegetation, and other parameters from making observation in these window regions. But when we want to make observation of trace gases like water vapor, then we make observation at these wavelengths where there is strong absorption by various gases like water vapor in this region, ozone at 9.8 micrometer, and CO2 at around 15 micrometer. So I will tell you how different parameters are retrieved by making use of those absorption bands. Okay, and this is in the infrared. But if you go to microwave, in the microwave region also, this is from 1 gigahertz to 300 gigahertz. You can see there are various absorption bands or lines. This is a weak absorption line because of water vapor at around 22 gigahertz. Then there is a strong absorption band around 50 gigahertz here, 60 gigahertz here, 50 to 60 gigahertz. Then there is one strong absorption band at 120 gigahertz because of oxygen again, and another strong absorption band due to water vapor around 180 gigahertz. So these absorption bands will be used to derive different atmospheric parameters, and that we will discuss in subsequent slides. So before that, this is very important to understand how radiation is passing through Earth's surface and passing through different layer in the atmosphere and reaching satellite. So that that is called as a forward problem that we can see here with this radiative transfer equation. That is the radiation or radiance which is reaching at the top of atmosphere or at the satellite altitude, is I lambda or I nu. This is frequency or lambda wavelength, whatever you call it. The first term is the contribution which is going from surface. So surface is radiating at surface temperature of Ts, that is surface temperature. Okay, and then you can construct a Planck function how much radiance is emitted at wavelength nu. And then because this is not a perfect black surface, is not a perfect black body, so you have to multiply by emissivity of surface. So this much radiance is emitted by Earth's surface, and how much is reaching at satellite, then you have to multiply again by a transmittance of atmosphere. So when you multiply by this transmittance, this first term tells you that how much radiation is emitted from surface which is reaching satellite. Okay, so this is contribution of radiance at satellite altitude from surface. Now, atmosphere is not transparent. If this was transparent, completely transparent, there will be no emission, no absorption by atmospheric gases. And if there is no absorption, it means there is no emission by the atmosphere. So in that case, you would only have the first term. But it is not true, because there are many wavelength bands where gases are strongly absorbing. This 13 to 15 micrometer band for CO2. This is around 9 micrometer for ozone, and there are various other this absorption band for CO2. So what will happen there? The gases which are there in the atmosphere will absorb radiation which is emitted from surface. Okay, and that part is absorbed, but the gas itself is at certain temperature, temperature of that layer, atmospheric layer. So the gas at that layer will again emit temperature or radiation. Okay, and that radiation emitted radiation will be given by the Planck function again. Okay, and the Planck function at temperature of that level. So if you integrate the individual layer radiation from a particular level to satellite sensor, that integrated amount will be the total amount of radiation which is emitted by different layer in the atmosphere and reaching satellite sensor. Okay, third term is not very much important here, because if a layer is emitting, it is emitting in both the direction, upward direction as well as downward direction. So downward direction again gets reflected by surface, and again it travels back to satellite sensor. So that it comes in the third term. But in infrared, the third terms become very, very small. Only it will be important in microwave, because emissivity in microwave will be very, very less than 1. Whereas in infrared, surface emissivity will be of the order of 1.99 precisely. So this term becomes very of the reflection term. So there are two terms which are contributing to radiation which is measured by satellite. The first term is which is emitted by Earth's surface, and the second term is integrated radiation, which is emitted by Earth's atmosphere. Now here you can just try to understand these three, how these radiation are traveling in the atmosphere. Solar radiation, where sun, is the solar radiation is the primary source of energy that gets reflected by various parts of the Earth. So maximum reflection occurs where there are deep clouds. So you can see bright patches here because radiation emitted is very, very large. Ocean, you can see when there is no cloud, it looks black, dark, because there is no reflection of visible radiation. So this image in visible or still region basically shows you what is the reflectivity, what is the albedo of different surfaces in the land or atmosphere. It will not show you anything else, but only the reflectance of Earth and atmospheric system. But if you make measurement in thermal infrared, there is no solar radiation because solar radiation is available only up to 3 or 4 micrometer and peaking at 0.5 micrometer in the visible region. But the thermal, infrared radiation typically which is emitted by Earth's surface, and Earth's surface typical temperature is about 300 Kelvin, and that gives you the peak radiation around 10 to 12 micrometer. So you can see that this is basically emitted radiation. Now here, if you see this, if you want to interpret this bright thing here, it means that the emission over this region, emission over clear region, is from warmer surface temperature, okay? Warmer land surface, warmer sea surface temperature, around 300 Kelvin, or even over desert, it may be about 330 or 340 Kelvin. So the radiation, amount of radiation which is emitted from these parts of Earth is very, very high. But if you go to clouds, cloud is at very, very high altitudes, like 10 kilometer and 14 kilometer, and temperature at those altitude is very, very low. So you can say that the emission which is happening at these regions is from a layer or from a surface which is at the temperature 200 Kelvin or 225 Kelvin. So the radiation, amount of radiation which is emitted from cloud system will be very, very less. Okay. So basically this image, if you see the image, that this should look dark, and this should look bright. But because we want to see cloud as bright, we invert those gray values, and we say that wherever it is bright, it is very cold cloud top, and wherever this is dark, it means the temperature is very, very high over those regions. So infrared imagery is giving you information about temperature, which visible imagery cannot give you. Okay. Similarly, if you go to water vapor absorption band, now water vapor absorption band is a band about 6.5 to 7 micrometer region, where water vapor absorbs this infrared radiation. Now, whatever radiation is emitted from Earth's surface is getting absorbed by the water vapor just above the Earth's surface. Okay, maybe at 500 kilometer, 5 kilometer or 10 kilometer. Now you cannot see anything below any feature corresponding to surface, because the radiation which is emitted by Earth's surface getting absorbed by immediately above the atmospheric layers. So what your satellite receives, it receives only the emission which is emitted by upper troposphere and this stratosphere. So what you are getting basically here is the water vapor features. There is a strong water vapor in the upper troposphere. So the water vapor features you are able to see here. So these are the smooth features are because of the water vapor presence in the upper troposphere. And you will be able to see only those clouds which are above those water vapor layer, and which are at very high, very larger heights, about 8 kilometer, 10 kilometer. You will not be able to see those clouds which are very near to Earth's surface, like these clouds you will not be able to see in the water vapor images. Okay. So this way we can make observation of temperature, about water vapor, and about various other trace gases in the atmosphere. So here we will focus only on some of the primary parameters. The first and foremost is temperature and humidity profiles, that is called atmospheric sounding. Then we will also discuss something about atmospheric winds, how we can derive atmospheric winds at different level in the atmosphere, and also at the sea surface wind. Then we will discuss about sea surface temperature, and similarly land surface temperature also can be derived in the similar way, and a little bit about rainfall retrieval. Now we have to keep in mind that when we are going to discuss about temperature, humidity profile, retrieval, or various other parameters, we have to keep in mind that what are those regions of electromagnetic spectrum which are absorbing those electromagnetic radiations. So you can see here CO2 is absorbing around 4 micrometer. Water vapor, this water vapor in atmosphere is absorbing around 6 micrometer. This is for ozone around 9.8 micrometer. CO2 from 15 micrometer. And then this I already discussed various absorption lines or absorption bands in the micro regions. Now we will start one by one. So first of all, when we make measurement in the different part of spectra, we can make this measurement at top of atmosphere in different wavelength. Wavelength at 4 micrometer, 5 micrometer, 6 micrometer, 5, 6, 7, 8, okay, 9, 11, 12, and then 13, 14, 15. If we make observation in these different regions, if we can have your radiometer working, making measurement of radiation at top of atmosphere in these different bands, also in these different bands in microwave. So what informations those observations are providing? So when we want to retrieve different parameters, okay, there are two methods. One is empirical regression, empirical methods, where you make simultaneous measurement, or you make a data set which is simultaneous measurement of in situ parameters, that is surface observation, with satellite radiance or satellite brightness temperature. So for example, if I'm making my satellite is making observation in 11 micrometer brightness temperature I have, and at the same time I have sea surface temperature or other parameter like OLR or like rainfall. So how I can make one relationship between the satellite observation and same time measured parameter, atmospheric parameters like water vapor, temperature, humidity, sea surface temperature. So if I make a large database of these type of matchup data set, then I can generate one empirical regression relationship. And these days, AI/ML methods are also very popular, where you can have even very, very large data set, and you can train your data set to give retrieval in future whenever you have satellite observations available. Now, if you want to stick to this first method where you want to have a matchup data set, then you have to wait for at least 6 months or 1 year after satellite launch to collect those simultaneous data of satellite observation and surface observation. Okay, so that for 6 months or 1 year, you will not be able to utilize that satellite data. But if you make use of radiative transfer model, these days radiative transfer models are very, very accurate. They can precisely compute the radiation expected at top of atmosphere by satellite if you provide exact information about atmosphere and land surface. Okay, if you provide exact information about land surface temperature or sea surface temperature, also the temperature profile, humidity profile, and various other gases in the atmosphere, it can exactly compute the brightest temperature or radiance which a satellite will be measuring at a different wavelength or different frequency. Okay, now what we can do here, we have passed several years of data available from MET agencies. You have radiation data, you have surface observations. So based on that observation, you can simulate your satellite sensor, satellite sensor observed brightest temperature or radiance. And based on that, you can develop an empirical or other type of machine learning algorithms to derive this atmospheric parameters in future. Okay, so this is very, very fast, because even before satellite launch, you only have to know what is your sensor characteristics. Okay, what are your sensor parameters, like what is the center wavelength and what is the bandwidth, what is the sensor response function at different spectral interval. If you have those informations, like noise equivalent delta temperature. So based on those lab measured the specifications of your sensor, you can simulate your satellite radiances or satellite brightest temperature well in advance, even before satellite launch. And you can prepare your algorithm for retrieval. And the first day, as soon as you receive the first satellite data, you can generate your atmospheric, you can retrieve your atmospheric parameter. Although there will be some bias in your satellite parameter retrieved this way, because there will be some bias in your radiation transfer model. Okay, so what you will do next, for next 3 months or 6 months, you will be again collecting this in situ data and making a matchup data with the satellite these observations, and based on that, then you can again run your radiation transfer model and compute satellite expected radiances or brightest temperature. So based on that, you can find out what was the bias in your RT model, and then if you incorporate that radiation transfer model dependent bias in your algorithm, you can get exact this parameter retrieval of parameter after 3 to 6 months time. Okay, and then you can say that my retrieval algorithm is now operational. There is a third category that is called physical retrieval. In physical retrieval, you are not using now statistics here. You are directly making use of radiation transfer model when your retrieval is taking place. Okay, these previous two things are radiation transfer model you have made use of before satellite launch. When you are making retrieval, you are not using radiation transfer model. Okay, in physical retrieval, once you receive a satellite measurement like brightest temperature or radiance in different channels, suppose you have 15 channel or 20 channels. Okay, now you have exactly at the time you have first guess atmospheric state that is coming from your forecast model. Also, NWB model can forecast for next 24 hours to 72 hours. So you have beforehand, you have a forecast atmospheric state which is coming from your NWB model. That may not be very accurate, but that you can say that is a first guess profile which is available to you. Now from that first guess, you compute satellite radiance using your forward radiation transfer model. Okay, once you receive that, once you compute that brightest temperature using radiation transfer model by from first guess profile, you match that with your satellite observation. If it is matching exactly with your satellite observation, then you can say that your first guess is the exact atmospheric state which you are looking for. Okay, and that is your final solution. But if there is a discrepancy in different channel, if there is a discrepancy in brightest temperature measured by satellite and simulated by RT model using first guess, then you can see that okay, this channel there is discrepancy. It means the parameter which is sensitive to this channel, I need to change that. Okay, so you need to change temperature profile or humidity profile in atmosphere. Okay, and then once you modify that temperature humidity profile, you can again make use of your forward radiation transfer model, and that is called your first iteration. Okay, in second iteration, you will again after adjustment, again you compute the radiance or brightest temperature, and then again compare with your satellite measurement. If at the second iteration, if you see that okay, now it is matching, then you will stop at that point and you will say that okay, the adjusted first guess is your final solution or final atmospheric state. Okay, if not, then again you go on iterating till you get a stable solution where the difference between simulated brightest temperature from first guess or modified first guess becomes very close to your satellite observed. And close means it should be within your noise sensor noise specifications. So this way you can go on iterating in physical retrieval, and then at the end of your iteration or your physical retrieval scheme, you get those parameters which you want to retrieve. For example, if you take atmospheric sounding, okay, in sounder, you are making measurement in number of channels. If you see from 3.5 micrometer to 15 micrometer, our insert 3D sounder, okay, so it has 18 channels making measurement. So this channel number 1 is about 3.8 micrometer, then 4 micrometer, 4.2 micrometer, 4.5, 4.6, 4.7. Then in water vapor absorption band, there are 3 channels at 6.5, 7, and 7.5 micrometer. Then 1 channel in ozone absorption band around 9.8 micrometer. Then this is thermal infrared split window. So two channel in your thermal infrared window channel. So at 11 micrometer and at 12 micrometer. Then at 12.5 micrometer, and then there are 5 channels in your CO2 absorption band, starting from 13.5 to 15 micrometer. Okay. Now, if you are making observation in these different channels, you can call that their brightness temperature at different channels. So what information will be carried in those channels, that we will explain here in, briefly in this diagram here. Suppose I focus on CO2 absorption band here. Okay, this is CO2 absorption band from 13 micrometer to 15 micrometer. Okay, now I have 5 channels here. One channel is at the center of absorption band, that is 14.5 or 15 micrometer, where absorption is strength is maximum. Okay, so if I simplify that absorption band, I can say like this: this is CO2 absorption band. This is peak of absorption, lambda 3 is a lambda 3. This is the weakest absorption, lambda 1, that is this point where there is very less absorption. And then there are intermediate points where absorption increases from this wavelength, lambda 1 to lambda 3. Now, if you focus on lambda 1, okay, that is the channel which is at this point where absorption is very, very less. What will happen? Whatever radiation is emitted by Earth's surface is able to reach satellite. There is no absorption, very small absorption. I cannot say no absorption, but very small absorption by intervening atmosphere. Atmosphere means there are many gases, okay, water vapor, ozone, CO2. But for this band, this absorption band, I am only concerned about CO2, because only CO2 is absorbing in this absorption band, and I will say that only CO2 is absorbing in this absorption band. So CO2 is not absorbing at this lambda 1, very small absorption is there. So entire thing, radiation which is emitted by Earth's surface is able to reach satellite. And because most of the things are transmitted, there is very small absorption. So there will be very small emission from intervening atmosphere that reaches top of atmosphere. That's why I show this strength of these arrow. No? This becomes smaller and smaller. So maximum contribution is coming from surface. But now I straight away, if I go to this band center, absorption center, lambda 3, where there is very large absorption by CO2, okay, which is this third case. What will happen? Whatever is emitted by Earth's surface immediately gets absorbed by CO2 within few kilometers. Okay, so nothing is able to reach satellite. Now the second layer, if you take second layer, whatever is emitted from this layer, that also gets absorbed within atmospheric layer above that. So what your satellite is receiving is only radiation which is emitted by top of atmosphere. So top of atmosphere, because after that there is no gas, there is no CO2 above top of atmosphere. So whatever is amount of radiation is emitted by top of atmosphere is able to reach satellite. Okay, but in between there is no radiation which is able to reach. This layer, the very small amount of radiation is able to reach top of atmosphere, means your satellite at this wavelength can see this atmospheric layer, but it cannot see this layer, and this layer. Okay. Now, if I talk about weighting function, okay, that is the contribution of radiation which is recorded by satellite, okay, at different wavelength or different channels. So this lambda, the weighting function of lambda 1 at this place will be this one. That is, the maximum amount of radiation is contributed from surface, and there is very small amount of radiation contributed by upper atmosphere. There is nothing from upper atmosphere. It means if any amount of temperature change you make here over upper atmosphere, there will be the layer, the radiation which is emitted from top of atmosphere. So any amount of change in surface temperature or a temperature at the first 1 kilometer, 2 kilometer, 3 kilometer height will not make any change in the brightest temperature of this lambda 3, this channel. Okay, here. Now similarly, if you can divide this entire spectra, this entire absorption band into many number of channels. In insert 3D or 3DR, we have divided into 5 channels. So you can have 4 or 5 weighting functions like 1, 2, 3, and insert we can have 1 weighting function here, 1 weighting function here. So that way, you are able to sample entire atmosphere in 5, 6 broad atmospheric layers, and temperature of those layers can be retrieved by making a brightest temperature measurement in the channels. Okay. Now, why I say that this will give temperature information, because the CO2 amount in atmosphere is well known. Okay. In this equation, there are 2 variables. One is temperature, another is radiance or transmittance of atmosphere. Okay. So if you know temperature, if you know transmittance of the atmosphere, that is CO2 is a well-known gas and well-mixed gas in atmosphere. So you know what is the transmittance profile of the atmosphere. So the only unknown quantity in that case will be temperature. So by making measurement in CO2 absorption band, you can invert those brightest temperature information into temperature profile in the atmosphere. And the method I have shown earlier is you can either make a statistical regression or you can make physical retrieval for retrieving those informations. Okay. Now, similarly, this is for temperature retrieval. Now, if you want to retrieve water vapor, okay, so in that case, you will be making use of these three channels which are in water vapor absorption band. Okay. Now, this absorption band is because of water vapor. It is from 6 to 8 micrometer. What these three channels will show you? It will now show you what is variation of water vapor in different layers in the atmosphere. Here, because in the temperature, you know the temperature profile you already know from your first guess or from your CO2 band. The only unknown now in that case will be transmittance in the atmosphere. Transmittance is directly related to the amount of water in different level or different layer in the atmosphere. Okay. Now, similarly, if you make use of the absorption in the ozone channel, okay, that will give you information about ozone in the atmosphere. So, if in this atmospheric sounding, to get information of temperature profile, you have to make use of number of channels in absorption band of a gas which is uniformly distributed in atmosphere and the gas where you know the mixing ratio very well. Okay, like CO2 and oxygen. Oxygen in microwave is very much useful for that point of view, because oxygen and CO2 are well mixed gas in the atmosphere, and their concentration you know very well, and that is not changing with time, not changing very much with time. Okay, but water vapor, ozone, and other trace gases, because their amount in atmosphere is changing drastically, so you cannot use those observations for temperature retrieval, but you can make use of those channels for getting information about various gases in the atmosphere. That is water vapor, CO2, CO, methane, and so on. Okay. Now, this is just one example of insert 3D, 3DR I'm giving here. These are the 18 channel brightness temperature which you receive. Now, channel number 1, 2, 3, 4, 5, they are CO2 absorption channel. Channel 1, you see the brightness temperature is very, very small, because this channel is looking at top of atmosphere in the stratosphere. This channel is looking at tropopause, about 15 kilometers. This channel is looking at, for example, upper atmosphere. This is looking at middle atmosphere. This is looking at lower atmosphere. And these three channels looking at surface. So by making measurement in these 5-6 channels, you can construct temperature profile in the atmosphere. Now, from this temperature information, now again you go to water vapor channels here. This channel number 10, 11, and 12. They are water vapor absorption channel. So this channel gives you the water vapor around surface, water vapor around middle atmosphere, and water vapor around upper troposphere. Okay. Then there are various other channels which also provides you information about temperature. If you construct a weighting function of these temperature channels here, you can see these are the weighting functions. What does it mean? That these channels can provide you temperature of this stratosphere, troposphere, upper troposphere, mid troposphere, and lower troposphere. And from these number of channels, you can retrieve temperature from surface to about 40 kilometer, 50 kilometer. So this is one example of our insert 3DR temperature profile retrieval. Similarly, by making measurement of brightness temperature or radiance in water vapor absorption band from 6 to 8 micrometer, these are the weighting functions, okay, corresponding weighting functions of these three channels. It means this channel will provide you the water vapor of upper troposphere. This channel will provide you water vapor of mid troposphere. This will provide you water vapor of lower troposphere. And there are other split window channels here. They will provide you information about near surface water vapor. So based on these observation in these channels, you can construct water vapor profile in the atmosphere. Okay. Now these are our this multispectral sounder. If you have hyperspectral sounder, where you are not only measuring these broad spectral bandwidth, brightest temperature, but where you are able to sample each absorption lines, like the black lines you can see here, they are spectra which your hyperspectral sounder on top of on-board satellite is measuring. Okay, if you can measure those spectra at top of atmosphere by your hyperspectral sounder, then your our temperature profile and humidity profile, vertical resolution will be very, very good. That I'll show you a little later. Get very good vertical profile of temperature and humidity. What do? You go for very high spectral resolution. For example, inside 3D or GOES or ATOP sounder, their spectral resolution was very, very coarse. So in that case, what will happen? Your temperature profile accuracy will be about 1.5 to 3K in entire atmosphere. Humidity, you can get only about 30% accuracy in the entire atmosphere. But if you improve your spectral resolution of your instrument, and if you go to ERC, METOP ERC, where spectral resolution is 0.3 centimeter inverse, okay, then your accuracy of temperature profile will be about 0.5 K throughout the atmosphere. And for water vapor, your accuracy will be 10 to 15%. So there is very big improvement when you go from multispectral sounder to hyperspectral sounder, okay, like this 3DR to hyperspectral sounder, and your accuracy will be very, very good. That will be very much useful for numerical weather prediction models. Now the next thing we will discuss atmospheric wind. Now next important parameter for NWP or weather forecast prediction is winds at different atmospheric level. Now this is very difficult to get wind profile over entire atmosphere, but some information we can get from clouds. Now if you look at imagery obtained from geostationary satellite, okay, like INSAT 3D or Meteosat or Himawari imager, and if you have a sequence of imagery every half an hour, okay, so about 10, 30, 11, 11:30, that type of sequence of imagery if you have, what you can do is you can track one small tracer. You can take one small cloud here or here, and suppose you have, this is the cloud, which you can distinctly identify that this is the cloud shape here. Now after half an hour, where will this cloud system move? Suppose this moves here, and again another half an hour it moves here. So you know that this cloud system is moving in this direction, okay? And how fast it is moving, you can also find out what is the centroid, what is the center location of this cloud here, what is the location here, and what is the location in the third image. So based on that, you can find out what is the speed of wind at that level, at level of cloud, and which direction that cloud system is moving. That will tell you which direction your wind is moving at that level, okay? So there are three important things here, steps here. That is, first is tracer identification. You cannot get wind here because there is no tracer here. So a tracer has to be easily identifiable in your subsequent images, which you can identify. You cannot look at the center image here, which is a very homogeneous cloud patch here. After half an hour, where that patch will be, that you do not know exactly. So it has to be this type of thing where you have equal distribution of clear area, cloudy area, low cloud area, like that, which you can subsequently identify in your coming images. Okay. Then you track in your subsequent imaging and find out your motion vector, okay, of that tracer. And then finally you have to assign height. You know that what is the speed of wind at this height, okay? But what is the height of that cloud? That you have to find out from your separate algorithm. And here, in infrared, the cloud top temperature depends upon cloud top height. So from that you can determine that what is the height of that cloud, okay? So that cloud top height will give you the height of that atmospheric layer where you have measured wind using this cloud motion vectors. Now here, when only this you will be able to you will be getting wind vector only where you have clouds. Over low cloud you will get low level wind. Wherever there are tall clouds, high cloud, you will get high level clouds. But where there are no clouds, you will not get any information. Now, if you go to water vapor imagery, so that is very, very, very important here. Water vapor imagery gives you water vapor features of about upper troposphere, that is about 300 HPA, about 7 to 8 kilometers from Earth's surface. Now, these features, if you, I'm not able to show animation here. If you see the animation of this imagery, you can clearly see which direction that water vapor tracers are moving. And from that, you know that where will be the wind direction. So here you have to track the gradients. Here you have to track the patches of clouds. In this water vapor imagery, you have to track the gradients, okay, gradients of water vapor. And based on tracking of those water vapor gradients, you know what is the wind speed at that layer. And that is called water vapor wind vector. When you combine water vapor wind vector and cloud motion vector, you call that as atmospheric winds, okay, atmospheric motion vector. So this is an example. You can see that different location. You can from 3D imager, you can find out wind speed at different level of atmosphere. Okay. So these are very, very important parameters for numerical weather prediction models. Now I'm only dealing with infrared part of spectra or infrared instruments here. The second important thing is sea surface temperature. Now sea surface temperature is another important parameter here. For that, you make measurement at the infrared window region 10 to 12 micrometer. Okay, so what the amount of emitted radiation in that in this wavelength band is proportional to the amount of radiation which is emitted by Earth's surface, because atmosphere is fairly transparent in this region. So you know that what is the radiating temperature of your skin or surface skin or land surface or ocean surface. Okay, but we cannot say that atmosphere is transparent. There is emission, there is absorption because of water vapor even within this atmosphere window. You can see that there are various absorption lines within this 10 to 12 micrometer atmosphere window also. Now, if you split this thermal IR into two, from 10 to 11, 10.5 to 11.5, and 11.5 to 12.5, you make the two channels. What will happen? One of the channel will have higher absorption of radiation because of water vapor, and this one will have lower absorption. Okay, so if you find the difference in brightness temperature measurement, that difference in the brightness temperature measurement in these two channels will be proportional to the amount of water vapor in the atmosphere. If there is no difference, it means there is no water vapor in the atmosphere, because both the channels are giving you same brightness temperature. If the brightness temperature difference is very, very large, it means atmosphere is loaded heavily by water vapor. And that difference, that difference in brightness temperature is used for atmospheric correction. And finally, you can have your retrieval algorithm like this. Sea surface temperature equal to this empirical relationship here, where A0, A1, A2, A3, A4, 5, they are empirical coefficients. And different terms, this first term is the primary term, that is brightest temperature of this channel number 5, 11 micrometer. Then there is zenith angle dependency. If zenith angle increases or decreases, your path length also increase or decrease, and brightest temperature will change based on that also. So you also have to correct for that zenith angle dependency. That is coming from the second term. Third term is the water vapor correction, atmospheric correction, and that is coming from this term here, T5 minus T6, difference in these two brightest temperature. The last term is actually the non-linear correction of this water vapor and sea surface temperature for one day, one complete day. All acquisitions have been made a composite here. Now, you will not be able to find SST wherever there are clouds. Wherever there are clouds, because in that region, infrared radiation cannot penetrate through cloud. So you will be only looking at cloud top features. So sea surface temperature will not be measured over those regions where there are clouds. Now where there are clouds, you are going to retrieve precipitation, rainfall. Okay. So now here, this how to get rainfall. So there are some crude methods to find out from geostationary this satellite imager data. So if you have infrared imager, you know that if cloud is taller and taller cloud, the brightest temperature will be lower and lower. And we also know that the taller and taller cloud or thicker and thicker cloud will have more rain. That is our empirical knowledge. Based on that knowledge, what we will do? We will divide this entire image into various grid cells, and we will try to find out what is the fraction of cloud which is having brightest temperature less than a certain threshold. And there are some well researched the method in literature. This is Arkin's method, where you say that you find out the fraction of cloud which is having brightest temperature less than 235 K, and that fraction you multiply by a constant here. So you will find out what is the quantitative precipitation index, the estimate or rainfall over that grid cell at that particular time. And then in geostationary satellite, you get every half an hour you get imagery. So you can accumulate that over one day. One day you will have 48 images. So you can accumulate, and you can also find out what will be total rain over one day. Okay. So you can also find out rain rate, and accumulated rain also you can derive from that. But this is actually indirect method, which is only based on cloud top temperature. And you also know that it's not necessary that even if cloud having a cloud top temperature of 210 Kelvin will be raining. It's not always true. And there is also cases when even the brightest temperature more than 235, like even 250 K cloud top temperature also may be raining cloud. So there are various other methods where you can correct for those things, and that is done with the help of some NWP first guess. You have NWP forecast, and from that forecast you have this vertical profile of water vapor and temperature. So from that you can adjust even this rainfall estimate, and you can improve your rainfall measurement over different grid cells. Now we will move into microwave techniques of parameter retrieval. Now in microwave, we are making measurement at different frequency, and I have shown you that this entire spectra, there are various absorption lines or absorption bands, and there are various other this scattering properties of this atmosphere. For example, if you see this sensitivity study for different parameters, okay, in microwave, basically we will be dealing with ocean surface salinity, soil moisture, sea surface temperature, sea surface wind speed, cloud liquid water, water vapor, and atmospheric profile. So what is the sensitivity of different parameter at different frequency of measurement? So you can see here, the highest for salinity, the highest sensitivity is around 1 or 1.4 gigahertz. Second thing, for SST, the maximum sensitivity is around 6 or 6.5, 6.6 gigahertz here. For wind speed, the sensitivity increases slowly, and the peak is around 10 gigahertz here, and after that it saturates. For water vapor, the sensitivity increases slowly. It is maximum around 22, 23 gigahertz. Again it dips, and then again it starts increasing, and again the maximum sensitivity again will be at 180 gigahertz that I am not showing here. The cloud liquid water, that is liquid amount, it is increasing continuously, 40 gigahertz. So different frequencies, observations are providing information about different parameters. For example, if you are making measurement at 1.4 gigahertz, you are basically getting information about ocean salinity, or over land you are getting information about soil moisture that I am not showing in this graph here. Then at 6 gigahertz, it's sensitive to sea surface temperature that I have shown here. 10 gigahertz for sea surface wind speed, 19 gigahertz for cloud liquid rain or wind speed, 22 gigahertz for water vapor, 37 gigahertz for cloud liquid rain or sea ice. Then 60 gigahertz, which is oxygen absorption band, that is used for temperature profile retrieval, that is atmospheric sounding of temperature in microwave sounder. Okay, so in infrared sounder, we were making use of CO2 absorption band. In a microwave sounder, we will make use of this oxygen absorption band, because oxygen is well mixed gas in atmosphere, that you know very well, and that band is around 50 to 60 gigahertz. So that is for temperature profile measurement. Then again 85 gigahertz for cloud liquid and ice, which because at this frequency there is large scattering by cloud liquid or ice particle at the top of atmosphere or top of cloud. 120 gigahertz again is sensitive to oxygen, so that is also for temperature profile measurement. And 183 gigahertz, another absorption band which is very important, that is used for water vapor profile measurement in the microwave region. Okay. Now one by one, if I go here, so if you want to measure sea surface temperature, then again you have microwave radiometer which is making measurement at 6 gigahertz, 10 gigahertz, 18, 20. If you combine these four and make one empirical relationship between SST and brightness temperature of these four channels, so you will get primary information of sea surface temperature from 6 gigahertz plus correction term. The 10 gigahertz will give you correction due to water vapor, wind speed. 18 and 21 will give you correction due to water vapor in the atmosphere. Okay, so the primary channel for SST is 6 gigahertz, and these three other channels are correction term correction for sea surface roughness and atmospheric water vapor. So from that you can get information about sea surface temperature. And important point here is that you can get sea surface temperature in all weather condition. Even if cloud is present, you can get sea surface temperature. You cannot get sea surface temperature only when there is heavy rain. So raining pixel only you will not be able to find SST. So for example, here you can see this is microwave SST. This is SST retrieved from the infrared technique which I described earlier, from 10 to 11, 11 to 12 micrometer. So here you can see the dot of cloudy parts, there is no SST retrieval. Now when you combine this brightest temperature SST from microwave and from infrared, you get a merged product of SST, which is equally good over entire domain. The second thing is rainfall. Now, as I discussed earlier, rainfall from in infrared, it's an indirect method that is only based on cloud top. So that is not very accurate. But that itself, that again will be very, very good product because geostationary imager are continuously looking at one particular region. So you can get long-term history of rainfall measurement. So climate parameter point of view, geostationary infrared measurement is very, very good. But polar orbiting satellite where you have microwave instruments, microwave radiometers, so that can provide you very accurate measurement of rainfall. Why? Because in microwave, the microwave can penetrate through cloud. So 85 gigahertz can penetrate only the top few kilometers of the cloud. 37 gigahertz can penetrate a little more, 19 gigahertz little more, and 10.7 gigahertz can even look at the bottom of the cloud. So by making measurement in these 4-5 channels, you can means the brightest temperature or the radiation is interacting throughout this column, atmospheric column, which is actually creating the rain. Okay, and then you are getting finally you are computing the rainfall which is falling at surface, primarily from the bottom of the cloud. So this is not indirect method. So this we can say that this is the direct measurement of rainfall based on microwave observations. So the accuracy is very, very good here. And then there are again active microwave instruments which can give you, the profile of rainfall. We know that what is the total amount of rainfall falling at surface, but which layer in atmosphere is contributing to how much rain, that also you can find out from this precipitation radar, that is the active microwave measurement. Okay, so you can see here, you can know that which of the atmospheric layer is contributing to maximum to the rainfall. Now in microwave, another important parameter is sea surface wind speed. Now you know that cloud motion vector or water vapor motion vector, which we discussed with infrared imager, that can provide only information about wind speed in atmosphere where there is cloud or where there is water vapor this motions. Okay, but over sea surface is very, very important because this is the region where flux exchange takes place from sea surface to atmosphere. How much moisture is being transported from sea surface to atmosphere, which is very, very important for your atmospheric prediction. Now, there sea surface temperature is very, very important, and that you can that sea surface wind apart from sea surface temperature is very, very important. And sea surface wind you can get from microwave measurements. Now there are two measurements. One is microwave passive measurement, and another is active measurement. In passive measurement, that is microwave radiometer. I discussed it here that even microwave radiometer, 10 gigahertz emission is actually sensitive to sea surface wind speed. Okay, because when sea surface roughness increases, it increases the sea surface emissivity, and your brightest temperature will increase even if there is no change in the sea surface temperature. Okay, so that information, a scatterometer, where a satellite is sending a microwave pulse towards sea surface, and then it is measuring the backscattered this energy, the energy which is backscattered in the direction of satellite. So first condition, if you see when surface is calm, sea surface is calm, there is no backscatter. This entire energy is scattered into other direction, specular reflection. But when sea surface roughness increases, and this sea surface roughness is increasing because of increase in wind speed. Okay, and now wind speed driven this capillary waves which are generated at the sea surface that causes Bragg scattering in the this. When there is very large wind, the backscattering will be very, very large. Okay, so what happens when there is no wind over surface, over this point, there is no backscatter radiation. When there is very high wind, there is very large backscatter radiation. So by measuring the backscatter energy at your satellite, you can infer that how strong will be the wind at the sea surface. Okay, this is from your active microwave or active radar method. Now you also want to get the wind direction. So to get the wind direction, you have to make measurement in two different directions, forward direction and up direction. Because if wind is blowing in this direction, in forward direction, what will happen? There will be large ripple in the forward direction and less in the backward direction. So if you make measurement in this forward direction, and then again if you make this measurement in the backward direction, your backscattered radiation will be different. Okay. So by making measurement in different directions, forward direction and backward direction, okay, and also at different polarization, horizontal polarization and vertical polarization, you can infer the wind direction also in this case. Okay, so by measuring this backscatter energy, you get wind speed, and by measuring backscatter energy in two different direction and two different polarization, you get the wind speed direction also. Okay, so you can see this is example of our own scatterometer on board OceanSat 3, which is recently launched, and you can see the entire global ocean. You can generate a sea surface wind vector here, and you can see that even in presence of tropical cyclone, because in cyclonic region you cannot see sea surface from infrared. So to see what is the wind speed at the surface, you only have to make use of a scatterometer, that is microwave active sensor. So you can continuously monitor how the cyclogenesis is taking place. Okay, and you can see, you can also track the intensity and direction of cyclone, and intensity, intensity is proportional to the wind speed at the surface, and that you are only getting from scatterometer wind. Now I'll just quickly summarize some of other parameters which you can get from microwave radiometer. So microwave radiometer, as I told you, that different frequencies will have different information. 6 gigahertz will have maximum information from surface temperature, that is sea surface temperature or land surface temperature. 10 gigahertz will have maximum information, some information for sea surface wind speed. 18 gigahertz will have some information for water vapor. You can see over ocean water vapor, wherever there is water vapor, you can see different type of shade of color. Then again, 23 is strongly absorbing for water vapor. So again, you can see water vapor get from 23 gigahertz. 36 and 89 gigahertz, that is sensitive to rainfall. So you can see wherever there is rain shell over oceanic region, ITCZ region, you find different type of signatures. So different making observation in different frequencies, you can get different parameters of the land surface and atmosphere. And some examples are here. From these microwave radiometer, you can get cloud liquid water, you can get land cover type, you can get rain rate over ocean and land also with some little lower accuracy. Sea surface wind speed, okay, sea surface temperature. Now this is only speed, this is not direction here, because this is from microwave radiometer, and from radiometer we can get only sea surface wind speed, and not the direction. And sea surface temperature here, and snow water equivalent also over different part of this globe. So the very important instrument. Now a little talk about Indian satellites. What are Indian satellites represent for meteorological applications? So this is this series of Indian geostationary satellite, starting from INSAT-1 series in 80s to INSAT-3D or INSAT third generation in this recent last decade. INSAT-3D was launched in 2013, 3DR in 2016, and 3DS next satellite in this series will be launched during next few weeks, next few months time from now. And these are the parameters which you can get from INSAT imager and sounder. And in future, we will be having JSAT2, very high spatial resolution, and then fourth generation, which will be advanced imager and advanced sounder concept here. From INSAT-3D, we are making observation in visible, sphere, MIR, water vapor, and split window several infrared bands. And what are the parameters we are getting here is OLR, sea surface temperature, upper tropospheric humidity, rainfall. That is, there are two products of rainfall, that is hydrospectral rain. Then this multispectral rainfall algorithm, and then wind speed, that is cloud motion vector, water vapor motion vector, and visible image motion vector. Okay, so those parameters. Apart from that, cloud mass, snow, atmosphere, this aerosol optical depth, and fog information from imager channels. And this MMDRPS, which we have developed a complete system for parameter retrieval from insert 3D imager and sounder, that is operational at SAC as well as IMD and New Delhi. So you can see there are so many products which we retrieve from imager. There are almost more than 32 products. And from sounder also we get temperature profile, humidity profile, surface skin temperature, total ozone, and then there are various other derived products you can see from this list. And then cloud properties. So one of the most important thing for forecaster is cloud properties, that is cloud top temperature, cloud top pressure, and cloud effective emissivity. Even imager also we have those cloud products available like cloud mask, and you can see here is cloud microphysics, that is the cloud effective radius and cloud optical depth. So those parameters are very, very important for nowcasting, which Dr. Charu just in previous lecture, she also explained how you can make use of those parameters into your forecasting. And these are series of low Earth orbiting satellite from India, and you can say I'm not going to detail of this list. I'll just quickly go through that OceanSat 3 series. OceanSat 1 was launched in '99, which was having OCM, that is ocean color monitor, and one 4-channel multi-scanning microwave radiometer, which I just described. Now you can see here OceanSat 2, which was launched in 2009, that also had again OCM 2. Then KV band scatterometer. This is our first scatterometer for sea surface wind speed, and then one radio occultation sounder for atmosphere. Okay. Now mega topic, which was a joint collaborative work with the French agency CNES, and microwave, Madras provided, that is microwave radiometer that provided us total pressure of water, liquid water, wind speed, and rain rate. Apart from that, Saphir was our first humidity sounder, where you can derive humidity in the different layer in the atmosphere. And important part here is you can get humidity profile even in the presence of cloud. Unlike insert 3D sounder, where cloudy region you cannot get atmospheric sounding. Now OceanSat 3, which is recently launched, you can see here this also has a scatterometer, high resolution scatterometer, then 13-band OCM, and 2-band sea surface temperature monitor for sea surface temperature, high resolution sea surface temperature. Unfortunately, right now SSTM is not working, so you only have a scatterometer wind from the satellite for atmospheric applications. And recently we have, as a technology demonstration, ISRO has developed one microwave humidity sounder. This is our first in-house developed humidity sounder, and this was only for demonstration purpose. It was built in a very less time, about I think 3 months time, and this is giving you very useful information in water vapor absorption band of microwave, around 180 gigahertz. So these 6 channels weighting function, you can see weighting functions starting from near surface to top of atmosphere, and they provide you brightest temperature emanating from different layer in the atmosphere. This is top of atmosphere, and this is a surface layer, lower layer, and then from these six brightest temperature informations, you can construct or you can retrieve humidity in different layer in the atmosphere. So here you can see this is humidity profile in the atmosphere. So this is better than insert 3D sounder in a way that you can even get in presence of cloud. If this was insert 3D sounder, you will not be getting any profile retrieved over this entire region because there is a strong presence of cloud. But in microwave humidity, you can get sounding over this region as well. All these data products you can get freely, you can download from MOSDAC, that is a Meteorology and Oceanographic Satellite Data Archival Center. This is data portal of our SAC ISRO, and you can register and get any amount of data freely available from this web portal. Little bit about international satellites, because we do not have so many satellites which can provide you entire information needed for weather prediction. Okay, this was one question also in the previous lecture. But so we have to make use of global satellites available, as in other international agency also make use of our satellite data. Okay, so one of the most important data here is, there are two series of satellite, METOP series, which is operated by EUMETSAT, and another series is JPSS, Joint Polar Satellite System by NOAA. So these two satellite systems, polar orbiting satellite, they have ascending time of morning, evening. This is having noon and midnight. So 6 times a day you can get data from these two satellites. Every 6-hour interval you can get very good data from these two satellites, which is used by numerical weather prediction model for assimilation, and that even our models also make use of these type of satellite data. So here you have infrared sounding interferometer, ERC, which is having about 8600 channels, 8400 channels. Okay, and I showed you in one of the slides that our the profile retrieved from hyperspectral sounder is very good. For temperature, it can give you about 0.5 to 1K accuracy, and for humidity, it can give you about 10 to 15% accuracy, as compared to other this broadband sounders. Okay, then this has microwave humidity sounder, advanced imager, and other. This is the scatterometer. So all sorts of information, atmospheric parameter information you are getting from this METOP series of satellite. That is temperature profile, humidity profile, then other atmospheric parameters, sea surface wind. Okay, other series is JPSS series. So this series also you have JPSS 1 was launched in 2017 and 2020. There are 2 satellites in orbit, and 3 and 4 will be launched in 2026 and 31. So these 2 satellite series have ensured continuity till 2040. This EUMETSAT as well as JPSS. Okay, so you will be having a variety of atmospheric, land, and oceanic parameters for various applications. So this also has this hyperspectral sounder. Okay, then microwave imager, microwave sounder. So variety of instruments are available for parameter retrieval. Then geostationary missions. The GOES satellites you already have. These are the previous generation. I will not go into this one. But this recent generation of geostationary satellite, GOES-R series of USA, this is very important to look into. That started from 2016. Okay. Now this GOES advanced imager have 16 channels, and at this resolution, spatial resolution is about 1 to 2 kilometers. Now it is unlike our imager where we have 6 channels with 4 kilometer resolution and every half an hour temporal revisit. This ABI can give you 1 full disk every 30 minutes, okay, every 15 minutes, or you can say 3 regional scan over every 15 minutes, or even 30 mesoscale imagery. If you want only over some small, say northern India, you can get every 30 seconds you can get 1 image. Okay, and it's not only image, but it also provides you various information about vertical profile of temperature, humidity, and other parameters on cloud. Okay, so you can call this as a pseudo sounder because this is imager as well as limited sounding capability, very similar to MODIS on METOP satellite. Now, next in is a geostationary satellite from Meteosat. So there also, if you go to the latest version, so they have 2 satellites, MTG-1, third generation one, that is launched in 2022, and second will be launched in 2025. Then they also have MTG-S sounding. So this is hyperspectral sounding from geostationary platform. So first time you will have hyperspectral sounder on board geostationary satellite from this MTG satellite, which will provide you 3-dimensional wind, because for wind you want continuous imagery from water vapor or thermal infrared. Now this hyperspectral will provide you water vapor imagery of different layer. So from that you can generate wind vector over different layer in the atmosphere, and that will be very important for cyclogenesis.